Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discuss about the synthesis of Longifolene, the 6th way of synthesizing Longifolene in the laboratory that we were discussed. And as we know that Longifolene is a hydrocarbon. Hydrocarbon means it is made up of by carbon and hydrogen, is known as a hydrocarbon, and it is a natural product. And as we know that natural products are exhibiting or they are associated with many medicinal properties. They can act as a drug also, like as a anti-tuberculosis, antibacterial, antifungal, anti-depression. So that type of the property they are associated, and that's why we are studying such a type of the natural product, and they are naturally occurring. We can obtain those natural product by the various parts of the plants. And as far as that Longifolene is concerned, it is a tricyclic, and therefore there is a challenge of making such type of the compound in the laboratory, and for that purpose you should know the method of making as a carbon-carbon bond, maintaining its stereochemistry, and you have to achieve that target molecule with minimum steps, and the starting material or the precursor which is readily available in the market. So by keeping all these things, and whenever the reactions are carry out the reagent, the availability of the reagent and the reaction condition, suitable reaction condition, and we should get the maximum utility of that atom, and so that there is a less waste products are formed during those synthesis. So that type of the synthesis are keeping in mind, and that's why there are the different ways of synthesizing Longifolene in the laboratory, and from that the which method or which out of that 9 ways which method is suitable or the which produce the good yield, and that can be adopted, that can be followed, or that can be utilized in the laboratory or in the industries for manufacturing such type of the or for the synthesis of that Longifolene. So today we are going to discuss the scheme number 13.13, that is a 7th way. This is the 7th way of synthesizing Longifolene in the laboratory, and this 7th way is described by schools by A.G. Schools and E.S. Pugh. So these two scientists, they had described these syntheses in the laboratory, starting from different starting material which are readily available, and the reagent which they have used is a well known reaction, because the main objective of this synthesis to make the new carbon-carbon bond formation, and these Longifolene has a 4 stereogenic center, and that's why it is optically active in nature. Now let's begin with what the starting material they have taken over here. They have taken, this is a starting material. Here is a OCS3 methoxy group at ortho position, and here CO2Me ester group which is at ortho with respect to this, or you can call it as this type of the methoxy group and this CO2Me. And this compound and then treated with the A reagent. A reagent, as we know that there are the different reagent, suitable reagent, so that we will get as a desired product. First reagent here is used one, that is lithium in presence of NH3. Lithium in presence of NH3, as we know that this is a very good reagent, it is known as a Birch reduction. Birch reduction, this is a Birch reaction or the Birch reduction. Normally lithium or the sodium in a liquor ammonia. So this is the reagent. Whenever the reagent is formed, that reagent is known as a first time discovered or invented by the scientist. The name of that scientist is Birch, and that's why name is given to that reaction is a Birch reaction or a Birch reduction. Reduction takes place, for example, in case of the aromatic compounds are there, you might be knowing, suppose as a aromatic compound, let me take here the two example which I am showing over here. Here is a OCS3, I am taking this one. This is suppose as a OCS3, methyl phenyl ether, suppose this one. But as far as this organic compound is concerned, OCS3, what type of the group present on that aromatic ring? It is a electron donating or electron withdrawing, that we will see over here. So let me draw here properly so that you can understood that Birch reduction. In many competitive exam you might come across with this. And now here the two groups generally present on this one we can take here is this is ester group generally. And now look at both the aromatic compound, no doubt about it, it is a stable one. When the Birch reduction is carried out on this compound Li in presence of NH3, and here partial reduction takes place over here. Partial reduction, what do you mean by the partial reduction? Means here are the three, even though there is a stable aromatic compound, but partial reduction takes place due to the presence of this Birch reagent. This is a Birch reduction, we can call it as. This is a lithium, the metal in presence of the liquor ammonia, and because it is a single electron transfer takes place over there, and that form as a partial reduction. Now, but remember, if you remember these two groups, you can remember the Birch reduction forever in your life. Why? Because one, where this group, as we know that, now tell me whether this group is electron donating or withdrawing. This group is a electron donating group. Electron donating group. And now C double bond O, and this ester group is act as a electron withdrawing group. Electron donating group or electron releasing group, they give the electron to the aromatic moiety so that the electron density is increased on it. And now this is electron withdrawing group means what? This double bond shifted from here to here due to the carbonyl group. Carbonyl group here act as a electron withdrawing group. It withdraw the electron density from the benzene ring, means that benzene ring found to be electron deficient like this, And when such situations are there, partial reduction take place by the Birch reduction, and what would be the product? So look at here carefully, the product should be formed like this, partial reduction, here double bond and here double bond, here is a OCS3. This type of the product if you predict, then it is correct. Remember, electron donating groups are there, so adjacent to that electron donating group there is a double bond, and here also this is a partial reduction only possible with the Birch reduction. So that you should remember here. Even though it is a stable, but it get partial reduction occurs due to the, and that's why it is a Birch reduction is very. Now here is the electron withdrawing group. If electron withdrawing groups are present, partial reduction takes place here also, but remember the product will be this one, C double bond O M E. Remember these two examples, because on aromatic ring there are two kinds of groups are present, either electron donating group or electron withdrawing group. And if electron donating groups are present, then we will get such type of the partial reduction. If electron withdrawing group present on the aromatic compound, it always gives the product like this. Suppose you have a example, this is a toluene, as we know that. You must know the nature of that substituent which is present on benzene, either electron donating or electron withdrawing, depending upon that type of the product is formed. Here lithium in presence of NH3. Look at here also, it is also the electron donating group, and if electron donating, the product must be like this, so that you can predict the product very easily. Here CS3 like this. So these are the thing, this is related to as a electron, what we can call it as a Birch reduction, and Birch reduction is used over here, because here is the electron withdrawing group also, electron donating group also, as well as electron donating group also present over there, and how the partial reduction takes place over there, that you will see later on. And now here the second reagent which they have used is then iodine, then here CH2 thrice, this thrice, then here the CS3, then CS3, then next one will be CH, then O, CS3 twice. That is the reagent they have used over here. Here CH3 and CS3. That is the group they have used over here. Now partial reduction, look at here, this double bond is shifted from here. Because always remember electron donating group is there, so double bond remains adjacent to that. If electron withdrawing, that shifted away from that, so that you are going to get the product over here like this. This is a product. Suppose this double bond remains as it is, and OCS3, partial reduction, and this double bond shifted from here to here. Then here is a, what you can call it as a compound which we are going to get here, this here the CO2 Me, and now here the iodine, this can be attached over there further. Here you can write CH2 thrice C, CS3, then CHO, CS3, then twice. This is the compound which we got after adding these reagent together with this. So this is the compound which we got over here. Look at here, This is the Birch reduction. After the Birch reduction, it is treated with this. We got as a this type of the compound. And now let us add here the B reagent. B reagent I am going to add over here. First one, NBS in presence of methanol. First one is a NBS in presence of methanol, OH. CS3 OH, that is a one reagent. Second reagent, I am adding here DBU. As we know that the structure of DBU, it is a sterically hindered base, that is 1,8 diazo bicyclo type of the compound formed over there. And the third reagent is used here. The third reagent will be H plus acidic treatment, and water is used over there, is crushed. And after doing all these things, what do you get? You are going to get the product over here is this one. This type of the product you are going to get here, alpha beta unsaturated compound, and then here is a double bond, and at this corner there will be a this CO2 Me, and this rest of the part is this one CH2 thrice, then here a CS3, then CH double bond O. This group converted into as a most reactive group, like as a aldehyde group. CH double bond O means aldehyde group. Now this compound, after, as we know that NBS means N-bromosuccinamide, and it provide the source of bromine, and DBU is a sterically hindered base which can abstract the acidic proton and then H plus, and that conversion of that methoxy group, or this is just like as a protected, after the protected aldehyde group it looks over there, and these get deprotected, so that aldehyde group is retained as it is by using a H plus and H2O. Just acid treatment, it gives the aldehyde group deprotection will takes place, and we will get as a this type of the compound. And now, and this compound further treated with C reagent, and the C reagent will be this one. This is a compound which I am writing over here, N, then NH2. Here let me show this arrow over here. This is a phenyl group, and another phenyl group which is exactly opposite. One phenyl group is above the plane, one phenyl group should be below the plane, and then heat treatment is given over here. Sometimes is shown by the symbol triangle, or just written as a heat as a word. So this is a photochemical reaction, and this after the photochemical reaction is very important here, because it form as a tricyclic compound over here. And after the treatment of this C reagent, what you are going to get? You are going to get the product over here, the product which you are going to get. This is the product which you are going to get over here. Now C double bond O, then CO2 Me. Here is a 2-methyl group which already over there, and then double bond is remains over here. So this is the compound which we got after the treatment of this, and that is a photochemical reaction takes place and tricyclic compound is formed excellently without any, by maintaining as a stereochemistry, and after that it is treated with the D reagent, and that D reagents are number 1 H2 in presence of palladium charcoal. As we know that it is one of the very good excellent reagent for reducing as a double bond a olefin into as a saturated compound. Then second reagent will be taken as a sodium hydroxide, and the third reagent which is taken acid. Then there is a evolution of carbon dioxide, CO2 is get evolved over there, that is the decarboxylation takes place over here. Now what are the function of this each and every reagent? When H2 in presence of palladium charcoal, this carbon-carbon double bond get converted into as a single, then sodium hydroxide will hydrolyze this ester group into as a acid, then there is a treatment of H, decarboxylation takes place, and you will get as a complete removal of this group from here, and finally you are going to get the product. Here is this one. Look at the product which we got over here. This carbonyl group remains as it is, Sem dimethyl should be over there, and here there is no methyl group at all. So these are the thing which we got over here, and after that, after getting this compound, this is the product which we got after treatment of this reagent, and finally as in a scheme, and finally as in a scheme 13 point, as in scheme 13.24, which, and finally you will get as a Longifolene, which we are going to get over there. You have to give here what you have to do. First one, here you take as a pH 3 Li, first reagent, and second reagent should be as a methyl iodide. What it will do, it will pick up form as a carbanion over there, and this is going to attack on that methyl, and third one use as a Wittig reagent like pH 3 P double bond CH2, you will get as a olefin, not olefin, that is a Longifolene, which is a target molecule which we are getting over here in this compound. Now NBS, as we already described that NBS is a N-bromosuccinamide, it provides sources of bromine, that NBS which we have used in a previous case, that is a structure of NBS will be this one, N is a Br, and this is known as a N-bromosuccinamide. Then DBU18 diazobicyclo undecane 7-ENE, that structure also we know that this structure of that DBU18 diazobicyclo undecane 7-ENE, here must be as a double bond. So this is a structure, one is a 6-membered ring, another one is a 7-membered ring, and that is a structure of that, and it is a nucleophilic sterically hindered base which is used over there. and an enantiospecific synthesis of Longifolene was done, starting with camphor, a natural product available in enantiomerically pure form that is represented in a scheme number 13.31. The tricyclic ring was formed in step C by an intramolecular Mukiyama reaction, and as we know that the Mukiyama reaction and all these things, I think with these are the reactions we have described, that is the seventh way, the how that are the remaining important key intermediate, how we are getting that we will see in the next lecture. Till then, have a nice day. Thank you.